Hello everyone, my name is Ibtihal BELAL. I'm a PhD student at Mohammed Sadiq bin Yahya University. Today I'm going to give a presentation about structural and magnetic properties of LCBMSO polycrystalline perovskite manganite. The presentation will be in 5 parts. First, I talk about origins and the history of perovskite. Second, I go to the perovskite structure and their applications. Third, I give the experimental procedure which I use to prepare the sample. And then I discuss the main results. Finally, I finish with a summary. Perovskite is actually the name given to oxide mineral calcium titanate. So this mineral discovered in the Ural mountain of Russia by the German mineralogist Gustav Rose in 1839, and this mineralogist shown in the bottom left. It is named after a Russian mineralogist Lev Perovsky. A whole family of materials with the same basic structure as calcium titanate were discovered. So the perovskites have a general formula, and this formula is ABX3. From the right side of this page is an image of a perovskite unit cell, with A and B are positive cations. A can be alkaline earth or rare earth metal, and B is usually a transition metal. When it's occupied by manganese, the perovskite name manganite, while X is a negative anion, usually oxygen. So, on the right side of this slide, we have ideal perovskite structure. However, a large number of sample perovskite display distortions from the ideal structure, and that can be seen in the image on the left. These distortions manifest as rotation or tilting of octaedra, distortion of octaedra, or distortion of A and B cations polyedra. Distortions are due to side differences between cations on the A and B sides. The most important here that these distortions play a crucial role in the properties of the materials, because if a structure gives you a specific property, you can target a specific structure to give you a property what you're looking for. So because of this research about mathematical equation to give a number called tolerance factor that links cation size in the structure to what structure will be predicted. So the table here on the bottom shows the tolerance factor in different perovskite and the structure which can adapt. Any molecule with degenerated electronic states will be unstable and will undergo a distortion which forms the system of lower symmetry by removing the degeneracy, as shown in those images. In this respect, the anti-distortion is expressed by this equation. Then we talk about double exchange mechanism, which is a type of magnetic exchange between two transition metal ions via oxygen ion. The electron transferring to certain central sites from the neighboring sites should have the same direction of spin at the central site. The double exchange is only possible between two cations with parallel spins, which ultimately leads to ferromagnetic alignment, also metallic behavior, as the image shows. So far, although the perovskite structure and property they can have, and how the composition can destroy the structure, now it's interesting to talk about applications of this perovskite. So here I show several applications in which perovskite can be employed, such as photovoltaic, sensors, batteries, and memory storage. The crystalline sample was prepared by solid-state method. The detailed description of the sample is explained in the following flowcharts. For the results, firstly we start by XRD analysis. The XRD pattern of the prepared sample is taken at room temperature and is shown in the figure on the right. According to the Rietveld refinement, using foolproof software, the sample exhibits a single-phase orthorhombic structure. The reliability factors justify the high quality of our refinement, and the estimated crystal size was found to be around 26 nanometers. It is notable that the lattice parameters follow this relationship. This signifies that our sample has an O-type lattice distortion, originated from the Young-Taylor effect. And those tables show obtained parameters from the Rietveld refinement. Secondly, we move to magnetization measurement. For the purpose of studying the magnetic properties of LCBMSO, we have measured the magnetization versus temperature with two modes, the zero field cooled and field cooled modes, recorded under 100 Oersted. We found that during ZFC mode, the magnetization increases to a maximum at temperature of 110 Kelvin and then gradually decreases. But during the FC mode, the magnetization curve shows a clear diffraction from the ZFC curve at temperature of 156 Kelvin. This diffraction could be due to the simple spin, reorientation, or spin glass nature. The FC magnetization has decreased and has intersected the ZFC curves at a temperature of 70 Kelvin, corresponding to spin reversal temperature. Our sample exhibits ferromagnetic to paramagnetic transition at a temperature of Curie equal to 148 Kelvin. The relationship between a constant of Curie and temperature in paramagnetic region should obey the Curie-Weiss law. The positive value of temperature of Curie-Weiss demonstrates the ferromagnetic interaction between the spins. The theoretical and experimental effective moments were calculated using those relations. The experimental effective moment is much larger than the theoretical one. This difference can be explained by the presence of ferromagnetic clusters in the paramagnetic region. In summary, the LCBMSO compound has been successfully prepared by solid-state method. Refinement parameters indicate the high quality of our compound. Magnetization curves show a diffraction between FC and ZFC mode, which could be caused by the simple spin, reorientation, or the presence of spin glass nature. The difference between theoretical and experimental effective moment values confirm the presence of ferromagnetic clusters in the paramagnetic region. Thank you for your attention. I hope you enjoyed the presentation.